Yeah, hello everyone. Today's lecture will be devoted to electric potential energy, and whatever I teach today and on Friday will not be included on the test on Monday next week. But I have to start to teach that concept of potential energy and electric potential difference because there is a lot of material to cover. So I hope you can hear me. Can somebody confirm?
We can hear you.
Thank you very much. So before I define electric potential energy and electric potential difference, I would like to very briefly explain how we calculate work done by a force. And you should know that concept, how to calculate work, because it was covered in high school and in Physics 1800 and in Physics 1801 as well. So for simple situations, when let's say like a typical box is acted by the force F and the box can move on the floor, and if the force is constant in terms of magnitude and direction, then the amount of work done by that force on the box we calculate as the dot product, the force dot displacement S. S is the displacement. Displacement is also a vector quantity. So the work is, and the dot product, of course, involves cosine function. So the work done by that force can be written as F cosine theta S, where that angle theta is the angle between the displacement and the force. So this expression, the dot product is to calculate work, is correct if the force is constant in terms of direction and magnitude during the displacement. And of course, you did this type of calculations many times in the past. But what about the case when the force is acting and the object is not moving along the straight line, but along certain curve, like what you see here on the slide? Then how do we calculate work in these situations? So what we would have to do in these situations, when the curve is not a straight line, but a curve, we would have to divide that curve, that path, into many tiny parts. Let's say one little part is indicated, we would call it ds, differential displacement ds, and we would calculate work done by that force during that tiny differential displacement. And then we would have to take another little displacement, another little displacement, another displacement, and so on. So in short, we would have to calculate work on tiny displacements. Each tiny displacement ds we could then treat as a straight line displacement, because if that ds approaches zero, then we can treat this displacement as now straight line. And so for each little path, we would calculate tiny amount of work, which we could call dw. So that would be the work done by that force during that tiny displacement ds. And that amount of work we could find as F cosine theta ds. And that could be written as F dot ds, where F would be then constant during the displacement. Okay, and then the total amount of work done during the entire path from A to B, of course, we would have to find as the integral of, which integration, as you know, is summation. So as the sum of these tiny works done on each tiny displacement. So the total work would be just integral from A to B, from initial to final point, F cosine theta ds, or written compactly as integral F dot ds. So this expression, F dot ds, is called vector line integral, because we integrate over the line. And we integrate the vector quantity. See that F, of course, can change in the displacement. Now, let's say here, the force might have different direction, be a different angle to the tiny displacement ds. So at every point, the force could change in magnitude, and it can change in direction. So in general, this type of integral is very difficult to calculate. We call it, again, vector line integral. And you will be learning in calculus 2015, although I do hope that you learned something about line integrals in calculus 1014 as well. But in mathematics, sometimes you will calculate line integral of the scalar quantity. So where that f, that function would be scalar quantity. But in physics here, the most important are these vector line integrals where that function under the integral is a vector quantity. So that is particularly difficult to evaluate because we have to take the direction and the angle between that force and the displacement into account. So that's how you calculate work done along a line. And any questions so far? So in short, when the path, when the object moves on a curve, on a certain path, not necessarily straight line, you have to replace this dot product when the force was constant with the displacement. Now you have to replace this by integration, which means by summation. We have to calculate work on tiny displacement and find the sum, means to find the integral. So any questions? No questions. So I then move forward and we will be calculating the work done in most cases by electric force, but for now I'm just explaining in general about any type of force F. But we will be calculating that work done by electric forces on this curved path, and for some of these paths we will be using the rectangular coordinates, which you are the most familiar with. In some situations it will be convenient to use cylindrical coordinates, and some calculations spherical coordinates. So I will get to these other cylindrical and spherical coordinates maybe in about a week, so that you have more time to learn about that in calculus courses. But for now, I will just explain how to evaluate that line integral in rectangular coordinates. So in rectangular coordinates, we can write the force always using these rectangular components, Fx, which is the x component of the force, Fy, and Fz, right? And I, j, and k, these are unit vectors. I along x, j along y, and k along z direction. So any vector can be written like this. You should know that very, very well from linear algebra, physics 1800, and physics 1801, that any vector can be written in components form. So this what is in front of I is x component of the force. This is the y component of that vector F, and this is z component. And in general, and you should be now, in general, that Fx can depend not only on x coordinate, but it can also depend on y and z. And in general, Fy can depend on x, y, and z. So in general, Fx, that x component can be, multivariable function depending on, on the situation. But anyway, for now, that force can be written using these components like that, and displacement can be written also using these unit vectors I, j, and k like this. So for example, if you would have displacement from point O to Q, and that would be that tiny differential displacement ds, where ds approaches 0, then this displacement we can also decompose into a component along. So this is what from P to Q is along the diagonal of that little cube, where that cube I drew, so that you see that this little displacement PQ, that displacement ds, I can decompose into displacement along x direction, which I call dx, into displacement along y, which is called dy, and displacement along z, which I call dz. You see, so that vector ds can be decomposed like this: dxi plus dyj plus dzk, and then the dot product, which we have to use to calculate work, f dot ds. Dot product, as you know, is the sum of first component of f times multiplied by x component of the second vector. So this multiplied by this plus this times this times this. That's how you evaluate dot product. First component times first component, second component, second component, third and third. So this is of course obvious. That was done in high school, not to mention about university courses. So once you write the dot product between force and displacement or like this, then the integral, yeah, and the work done along any path can be written as the line integral f dot ds from initial point to final point from A to B. Now the dot product I can replace by this expression, you see. So this will substitute the dot product, and then I can integrate along x, along y, along z direction separately, right? Where point A would be having coordinates xa, xb, xa, ya, and za, and point B would have coordinates xb, yb, zb, right? You need 3 coordinates to specify position of the point. So and you would integrate from initial coordinate x to final coordinate x, from initial y to y, and z, initial to z, final. That's how you would evaluate the work using rectangular coordinates, even if the path is complicated. So this is general expression how to calculate work done by the force. And this is very simple thing to do if fx depends only on x, because then instead of fx, you would have certain function of x, and you can integrate this. The same, if fy depends only on y, then you can integrate along y. And the same, if fz depends only on z, that's this integral is also easy, right? So, but the complication occurs if fx, let's say, that x component of the force depends also on y and z, which can happen. Then in these cases, we have to know the equation for that path of the displacement. We have to have whether displacement along the straight line or parabolic line or whatever line, we have to have that equation. And then now it's a little bit more complicated. But as you will see, for electric force, which is conservative force, and I will explain in a minute what means by conservative force, we will be able to always evaluate these integrals like this. First integral just on x, so the second only y and z, and the other coordinates we can keep constant. So that I will explain details later on. For now, I'm explaining everything in general terms. So before you ask questions, I would like to give you example how to do it in practice. So the next slide is the example. Let's say that we have to calculate amount of work done by the force F, which is given by this expression. Okay, what does it mean? That whatever is in front of unit vector I is Fx. So this is x component of force F. This is x component. And as you see, x component depends only on x. This, whatever is in front of J unit vector is Fy, y component. But as you see, that y component depends on z, not on y, but on z. And the third component, which is what is in front of k, is 1. That z component, of course, is equal just to 1, right? So x component is equal to x, y component is equal to z, and z component is equal to 1. So then my dot product, so when I want to evaluate now the work done by that force F, when the object moves from initial point A, I should have written, yeah, point A with coordinates 1, 2, and 3, to the final point with coordinate -2, 4, and 5. And if that displacement is along the straight line, so displacement is along the straight line given by this equation. So this is the straight line equation. You should be able to recognize that this is the straight line equation, that z is equal y plus 1. Right, so this displacement would be in zy plane. There is no x here. So this displacement is in zy plane. The slope, what is in front, so of y, it would be slope equal to 1. This is intercept. So this is along this type of line displacement. So I can replace this integral by the sum of these three integrals. So this is not the triple integral. This is the sum of three integrals. I calculate like from the previous slide, right? You remember. So this was fx dx, but fx is equal to x. So I substitute x dx, and I have to integrate from x coordinate of initial point, which is 1, that's the initial x component, to the final x coordinate, which is -2. So from 1 to -2. Then the second term would be, I have to integrate this, which is fy, right? And fy is equal to z. But z is equal y plus 1, right? Z is equal to y plus 1. So I substitute. Fy is actually y plus 1 dy. And I integrate from initial y coordinate, which is 2, to the final y coordinate, which is 4. So from 2 to 4. And the same with z. Z component is 1. So 1 times dz is dz from 3 to 5. From 3 to 5. And then you integrate, evaluate each integral. The first one is, of course, x squared divided by 2. And you substitute upper limit, lower limit. The second integral is, of course, y squared divided by 2 plus y from 4 to 2. And the third integral would be z, and limits are 5 and 3. And then you integrate each term separately, substitute upper, lower limit. You evaluate them, add to these three numbers, and you get 23 divided by 2 joules, because unit of work is joule. So any questions about this simple example? Any questions? No questions. Again, I take this as a good sign. So we will go.
Sorry.
Yes, please.
For the z at the very end, once it's integrated,
yes,
the z bracket 5, 3, do we replace the z with the y plus 1?
Yeah, you substitute upper limit, so would be, so this integral would be equal 5 minus 3, right? Upper limit, substitute for z 5, so 5, and then minus substitute lower limit.
Okay. You don't substitute the z for y plus 1 because z equals y plus 1.
No, only you. So this is the result of this integral, right? This is the integral. This is the result.
Okay.
Yeah, and this is, of course, the result of this integral, of this one. Right? So integrate one by one. And x, y, and z, these are variables.
Okay, got it.
Yeah, so we will be calculating the work done, in particular, done by the electric force. So for now, I'm just explaining in general, just to explain that initial concept about the line integral. So additional questions? Yeah, if you don't have questions, that's really good. So let us now talk about the electric force. So as you know, the electric force, we can always write like Q times E. So if we know the electric field, and now there are different ways to calculate electric field using Gauss law for some situations, or regular integral. That's what we have done in previous lectures. We calculated electric field in different ways. Once you know electric field, how it's changed in space, then the force you can always write as Q times E. Q times E. So if the charge Q is moving in the electric field, then of course the charge will move because there is a force acting on it. So Q times E would be the force. And then the work done by the electric force, we calculate all like I've explained as the integral F dot ds. And this is general expression. Instead of F, I substitute Q times E. Q is constant. So I can take Q in front of the integral, and then the work can be always evaluated or using this integral. E dot ds, but E dot ds I can substitute as E cosine theta ds, where theta would be angle between vector E and the displacement S. Right? So that is the general expression how you would calculate work done by the electric force. And that would be the line integral about any curved line from initial point A to final point B. So let us use this integral, but for the very simple case, when the charge moves in a uniform electric field first. So in general, of course, electric field, as you know, can change in space. But for now, my assumption is that electric field is uniform in space and indicated by these black parallel lines. And let's say that the charge Q0, I don't know this Q0, is moving from initial point A to point C, then to point B, and then back to point A. And we will now calculate how much work is done by the electric force when that charge is moved in that triangular loop. So of course, the charge will not move by itself, right? In that triangular path. Of course, I would maybe have to take my fingers if I could grab that charge and move it from A to C to B to A, right? I could move that charge, but I want to calculate amount of work done not by me with my hand, but how much work is done by electric force when that charge is moved by me in that triangular loop. And you will see that the amount of work which I would have to do will be of the same magnitude as the work done by the electric force, however, with the negative sign. If I do positive work, the electric force will do negative work of the same magnitude. Or if I would do negative work, then electric force would do positive work, but magnitude would be the same, as you will see in a minute. So the charge is moved by me in that triangular loop, but I want to calculate work done by that electric force, So you see, when the charge moves from point A to B along the straight line, in the uniform electric field, the force acting on the charge will be always constant as well, because electric field is constant in space, which means that the force will be always constant in space. If my charge Q0 is positive, the force acting on that positive charge will be in the direction of electric field, and that force will be just equal Q0 times E, but in the direction of electric field. But the displacement is along the straight line from A to C. So the angle between displacement and the force is here designated here and designated as pi minus theta. Why? Because that theta is taken to be this angle. If this is angle theta, then this angle, of course, remember, so this angle would be theta, right? This angle is equal to this angle. That is like Z pattern, you see? Like you see the Z, or I draw you Z pattern like in elementary school. You see, like this is Z pattern. So this angle is equal to this angle. Okay. And if this angle is theta, then this must be 180 minus theta, because this is 180 degrees. So understanding this, that the angle between displacement and the force is 180 minus theta, where this is angle theta, then the work would be equal, now because force is constant, so I can use just the dot product. So it would be force, Q0 times E, cosine of the angle, which is pi minus theta, times displacement from A to C. And this integral is just the displacement distance from A to C, right? Because integral ds is S, and S is from A to C, and A to C I can calculate, because in this triangle, this is L, from A to B is L, and this angle is theta. So the hypotenuse of this triangle, which is distance AC, would be equal L divided by cosine theta. So I've expressed the distance from A to C as L over cosine theta. But at the same time, I replaced here, you have to pay attention, instead of writing cosine pi minus theta, I have written negative cosine theta, because all of you should know that identity, that cosine 180 or pi minus angle theta is equal to negative cosine theta. Okay, that was done in high school, not to mention about university. So here is the negative sign, and then the cosine here and cosine here will cancel, and the total work done by that electric force will be negative. You see, negative Q0 EL. It is negative because the angle between the displacement and the direction of the force is larger than 90. So the work done will be negative work done by electric force. I would do positive work to move that charge, but of that magnitude, I would do amount of work of that much, but positive, and electric force would do negative work. Now, then I can also calculate in the same way how much work is done by electric force when the charge is moved from point C to B. So in this displacement, the force is always parallel to the electric field. So this is the direction of the force down, but displacement is horizontal. So as you see, the angle between the force and displacement from C to B is 90 degrees. Cosine of 90 is 0, which means that the work done by the electric force from point C to B will be equal to 0, because cosine of 90 is 0. And then we can calculate work from B to A. So here the charge Q, positive charge Q, is moved down, that Q0, which is positive, moves down, and displacement is parallel to the electric field. So from B to A, the work would be equal Q0E, cosine of 0, and times the distance from B to A. That integral ds B to A is just distance BA, which is L, which is designated L. So here the electric force would do positive work. And when I move the charge with my hand, I would do negative work. So the total work done by electric force is the sum of these three works. Negative, which was from A to C, 0, which was from C to B, and plus work Q0EL from B to A. The total work is equal to 0. I remember we did the same example in Physics 1801. I'm doing it again because it's so important that when the charge, any charge is moved in a closed loop in static electric field produced by static charges, the work will be always equal to 0, no matter what is the path. So even if I would select to move the charge along this loop in that uniform electric field, no matter how complicated, the work done by electric force on any loop in electric field is equal to 0, even if electric field is not uniform. You see, I selected that electric field to be uniform to make calculation easy. But even if electric field produced by different type of charges is not uniform, the work done on a closed loop, when the charge moves on the closed loop, the work done by electric force will be always equal to 0. Now, so to prove it in general, that requires quite a lot of mathematics. I hope they will prove it to you in calculus courses for that complicated arbitrary shape of line integral. But as I'm saying, this is always true. So whenever the work done by certain force on a closed loop is equal to 0, these type of forces we call conservative forces, as you remember from Physics 1801. And that concept of conservative forces is of huge importance. So I repeat again, if the work done by the force on a closed loop is 0, that type of force is called conservative. And you did talk about conservative forces in Physics 1800 as well, because gravitational force is also conservative. So you should be familiar with that concept. On the next slide, I summarize that important conclusion that the work done by electric force on any closed loop is always equal to 0, but with one important qualification, that this electric field that is that static electric field. Static means produced by static charges. In the future, we will talk about induced electric field. That induced electric field will be oscillating electric field. That electric field is not conservative. So only that static electric force due to static charges is conservative, right? And so far we talk only about electric field produced by static charges. Yes, please.
I'm sorry, I just have a quick question here. So since the force is conservative, so it means that it doesn't depend on the path, right?
It doesn't depend on the path. That's a very important observation which you've made. because the statement which I'm making right now, that the work done on a closed loop, when the charge moves on a closed loop in any static electric field, the work will be zero. But that statement is actually equivalent to say that the work done by that electric force is independent on the path. So this is explained on the slide here, that if I move the charge Q, positive charge, let's say Q, from point A to B along this path, complicated path, or this path, or any path, no matter how complicated, from A to B, the work done is the same for each of these paths, no matter how complicated is the path. The work will be only dependent on initial position of the charge and final position of the charge. But it does not matter how you get the charge from point A to B. It will not depend on the path. So these two statements are equivalent, that the work done by the electric force on a closed loop must be zero, you see, equal to zero, always, is equivalent to say that the work done by electric force is independent on the path from initial point to final point. The work only depends on initial and final point. So that's a very important observation. And I repeat again that only that static electric force now is conservative. But in the future, we will be talking about induced electric field. You will see that when magnetic field change in time, it will induce electric field in time will change in time. That induced electric field, that time variable electric force is not conservative, as you will see in the future. Okay, so I don't want to. So for now, we'll be talking only about electrostatic situations. So so because the electric force is independent on the path, then when we calculate work done by electric force, which is, remember, Q E dot ds, and Q I took in front of the integral because it's constant. So if that charge Q is moved from A to B, then the electric force will act, and that electric force equal Q times E the work will be independent of the path, which means that I can always replace this dot product as Ex dx, Ey dy, Ez dz, and integrate now from initial X coordinate to final, initial Y to integrate like I explained on the previous slide. And that path of integration is independent. So what I'm really saying right now, which is very important, but I will be repeating this again and again and again and again, is that integration can be done one variable at a time. One variable at a time, which means whenever, as you will see in the future, when you, for example, evaluate this integral, we will keep X as independent variable, but Y and Z will be taken as constants. And here, when we integrate this along Y, we will be taking Z and X as constants. So we will integrate one variable at a time, as you will see in the future. And that makes that integration very easy. And that can be done only for these conservative forces. Okay, so as I'm saying that, for example, even if that Ex, let's say, even if the Ex would depend also, let's say if Ex would be equal 3x squared minus YZ, let's say. So if that X component of the electric field would depend on like this, then Y and Z you would keep constant here. Integrate over only Y, only X. So even if Ex depends on X, Y, and Z, Ey depends on X, Y, and Z, and Ez depends on X, Y, and Z, you will integrate one variable at a time, as you will see in the future. That makes that integration very easy. So these conservative forces are of huge importance. And calculations for these conservative forces are particularly simple because of that. So I'm making few steps ahead, but you will know in the future what I really mean by explaining that we will be able to integrate one variable at a time. So any questions for now about that conservative force and meaning of conservative force?
I have a question about like the way that the integral is set up, because I thought because usually ds is used for surfaces, correct?
No, this is a very good question, because yeah, I understand now your question. So let me return to this slide, the previous slide, this slide. So remember, because in some textbook, like in your calculus, very likely in your calculus course, they designate ds as the surface element. But in physics, in my lectures and in your textbook, they designate surface area by symbol A, dA. That was the surface element. But ds in your textbook and in my lecture notes would be the element of the path. So this is the path, element of the path, not the surface.
So in comparison to the calculus textbook, then it would be like dr.
Yes, yeah, maybe in calculus you use dr, yeah.
Okay.
So I'm using the same symbols as in the textbook, and I would like to tell you that in physics, usually that path element is designated ds, and calculus probably dr. But surface area in physics we usually designate by symbol dA. Although there are many textbooks in physics where they use surface element like also ds, like capital S like this. So now different authors, different people in different textbooks, they use different symbols. But to clarify, I like that you asked that question. So ds is the element of the path, of the line, of the line.
Sorry, I had a follow-up question.
Yes, yeah, go ahead with your follow-up question.
So then would calculating the work be the same as parameterizing the curve of the, if it wasn't closed, and then taking, if you took the parameterization, then the derivative multiplied it by the force, then it would be the same as finding the work done by just the one curve?
Yes, that is correct. Because if the path of the charge, when the work is done on the path, then that line on which this moves will in general depend on x, y, and z, right? Or as I'm saying, or in spherical coordinate on r, theta, and phi, and so on. But in coordinate x, y, and z. And then usually that path, like you said, is explained using the parameter, let's say t. So x is kind of a certain function of t, where t is not time. T would be certain parameter, so you say is parameterized. Y would be written also as certain function, maybe g, in terms of the same t, and zt. So usually that's how it is done, right? That you express these coordinates x, y, and z in terms of a separate parameter, and then you integrate over that parameter. As you will see in physics, very often, the electric field has either spherical symmetry or cylindrical symmetry. And that you should know it already from lectures, that the electric field due to line of charge or in coaxial cable, usually that electric field has cylindrical symmetry. And then cylindrical coordinates are very useful. Or if the symmetry of the field is spherical, then it's very useful to use spherical coordinates. Mm-hmm. So actually, but in some kind of artificial cases, like if the curve is very complicated, then you would use some parameters like t, like you do in calculus. So this is all very correct.
Thank you.
Yeah, you're welcome. Okay, so I'm going back to my slide. So that was explained about the meaning of the conservative force, very crucial concept. But now, once you understand how to calculate work and what is conservative force, I would like to now define electric potential energy. Electric potential energy. And you should know again, from physics 1800, where you defined gravitational potential energy, and from physics 1801, when we defined electric potential energy, that potential energy, whether gravitational or electric potential energy, is only possible to define potential energy because gravitational force and electric force are conservative forces. So potential energy can be only defined when the force associated with that energy is conservative, either gravitational force or electric force. Because the potential energy depends only on initial position and final position. So as you remember, when you define gravitational potential energy, you use the mgh, right? That expression mgh. So if the object of certain mass moves from initial point to final point, it doesn't matter on which path the object moves. What matters is only the height difference between initial point A and final point B, right? That height, right? So gravitational force is a conservative force, and for that reason, gravitational potential energy was defined. Now, the same with electric force. In physics 1801, I should say, we have defined electric potential energy because electric force is also conservative force. So I wanted to say that potential energy depends only on initial position, final position, but it doesn't depend how the object gets from initial to final. It doesn't depend on the path on which it gets from initial to final point, right? Because that force, whether gravitational or electric, is a conservative force. So here I have now situation to again, that was all done in physics 1801. But imagine that I have electric field. Let's say it's now uniform electric field, maybe produced by two metal plates. This is, say, one metal plate, and this is the second metal plate. So electric field between these metal plates would be uniform. And let's say if the charge Q moves from point A to B. So if charge Q would be released, the charge would be acted by the electric force, would start to move, gain velocity and kinetic energy. So kinetic energy would increase because the charge would move spontaneously from point A to B. So when kinetic energy increases, then potential energy has to decrease, right? So the charge in electric field would have potential energy, and when kinetic energy increase, that electric potential energy would have to decrease because of the conservation of energy. So when the charge, positive charge, moves from point A to B in the direction of the field, its electric potential energy has to decrease because kinetic energy would increase. So whenever positive charge moves in the direction of the field, its potential energy decreases. But on the other hand, if the positive charge would be moved in this direction against the electric field from in this direction, then potential energy would increase. Of course, I would have to push that charge. I would have to take my hand and push that charge. I would do positive. I would have to push the charge, and all that work which I would do would go to increase the potential energy of the charge. So what I was explaining to you in physics 1801 was that whenever charge is in electric field, it has electric potential energy, and that potential energy will change when the charge moves from one point to another point. But that change of potential energy, which I here designated by delta U, that change of potential energy is equal to the negative of the work done by that electric force. So if you calculate work by electric force and change the sign, that will give you the proper sign of the change of potential energy. And we will be always calculating just the change of potential energy. Only change of potential energy has sense. So the change of potential energy between 2 points, A and B, let's say, I designated by delta U, and it is equal to the negative of the work done by electric force, which means this, that if electric force do positive work, because of that negative sign, potential energy will decrease. But if electric force does negative work, then the negative and negative will give you positive, and potential energy will increase. So for example, like in this case, the charge is positive, the force acting on it will be F equal Q times E. That force will be in the direction of the electric field. That force will move the charge from point A to B. That force will do positive work. due to that positive work, kinetic energy will increase, but potential energy will decrease, because you see the electric force to move the charge plus Q from A to B will do positive work, but potential energy will decrease. So that's the reason why I have to put negative sign in front. So this negative sign guarantees to me that the change of potential energy, delta U, will be correct, either positive or negative, but with correct sign. So if the electric force does positive work, because of this negative sign, potential energy will decrease, right? So that's the meaning of the negative sign. And questions?
Yes, I have a few questions.
Okay, a few. Okay, I hope not 10.
No, not that much.
Okay.
So from the formula here, it says delta U equals negative W. Does that mean that work 2 doesn't depend on the path?
No, it does depend. It doesn't. Yeah, the work done by electric force does not depend on the path. And that's the reason why we can define that potential energy. But what this expression here means is that when you calculate work, that the W is the work done by electric force. So here I have written, you see EL, so that you remember this is the work done by electric force. And when the work done by electric force is positive, like in this case, you see, if the charge Q is moved by electric force from A to B in the direction of electric field, potential energy will decrease. So final potential energy will be smaller than initial potential energy of that charge. And for that reason, I have to insert that negative sign.
Okay, yeah, I get that now.
Yeah, very good. And the second question?
Yeah,
okay.
So what if the positive charge goes from the first end to the second end, from point A to B?
Yeah, so if the positive charge is moved from A to B, potential energy will decrease. So potential energy delta U, which would be potential energy at point B minus potential energy at point A. And you always remember, delta U always calculate final position of the charge minus initial position. This will be negative. You see, it will be less than 0.
Okay, so my question is like, what if it's a capacitor type thing and like there's a plate there, so the charge won't be able to move anymore?
Yeah, well, if you would have like capacitor, if there would be a one metal plate and this would be second metal plate,
yes.
So the charge Q would move, would hit, if this would be positive plate, this would be negative plate, then this charge would hit the plate and that charge would be absorbed by that plate. Because in that metal plate, there are billions and billions, like maybe 10 to 23 atoms. So even if you add few billions of them, nothing will change on that plate, right? Because the number of atoms and charges in that plate is so enormous that even if now some charges, let's say some electrons, extra electrons, some other ions hit that plate, nothing will change.
Okay. And my last question.
Okay.
The force to move the charge from point B to point A, do you add that? Do you include that in the formula when you're calculating work done? This
is a very important question, because you see, if the charge would be here, and if that charge we move from B to A, then of course, remember, the electric force will act in this direction. That electric force F is equal Q times E will move in the direction of the field. So the charge by itself would never move from B to A. There would have to be external agent, we say in physics textbooks. Somebody would have to push that charge to the left. And then if I push it, then the charge could get from A to B. I would have to do some work to move that charge. But the work done, so I would do, by moving that charge, I would do positive work, but that electric force would do now negative work, right? Because displacement would be to the left, the angle between the force and the electric force would be 180 degrees. Cosine of 180 is -1. So the electric force would do negative work. I would do, by pushing the charge with my hand, I would do positive work, but electric force would do negative work.
Okay, so that means
so the work done by electric force when the charge would be moved from B to A would be negative. The work would be negative, and this negative minus and minus would give me plus, which means that the potential energy would now increase. Delta U would be now positive. Because yeah.
So does that mean that we only look at the force, the work done by the electric field? We don't look at any external.
Yes, we will be always considering the work done only by electric force and not by external agents, but to make sure that this change of potential energy is positive or negative with correct sign. You will always have to insert the negative sign, but this work will be done by electric force, like you stated. So we'll be always calculating work done by electric force, but that work done by electric force can be positive or negative. And this negative sign here will guarantee that the sign of the delta U will be correct.
All right, thank you.
Because delta U can be, change of potential energy can be positive, or change of potential energy can be also negative, right? So this negative sign will assure us that the change of potential energy will be correct. So excellent questions. These are very important concepts. Many of these things I know were done in Physics 1801, but it's very important to repeat them again and again so that all students understand that very well. So hopefully everything is now clear, and then I will do something else on the next slide.
Hi, Professor. I have a question.
About the previous slide?
Yes.
Okay.
When we calculated, because this is a conservative force, and so it's F dot ds, and then like we all like the potential energy difference is mostly dependent, like it's not depend. Is it correct that it's not dependent on the amount of charge we move?
No, the amount.
Oh, it is. Sorry, it
depends.
is.
It's clearly written Q.
Yeah, it is.
It depends on Q.
So, so like is it like minus Q times delta V?
Yeah. So we will get to delta V. I officially on the next slide I will define the electric potential difference delta V. So you're asking that question a little bit too early.
Sorry, and I have another complementary question about this.
Okay.
Because this is like exactly the same way gravity works.
Exactly the same. So whatever I explained about electric forces, in very analogous way, I could explain about gravitational force, right? Where the force of gravity would do the work. So instead, like here, instead of electric force, you would have to use that electric force, the gravitational force. But it's complete analogy between these two concepts.
So is this why like at every point in space, if you have an electric field, you have stored energy, and that stored energy can like do the same things as like when there's gravity? Because like I heard that if you have like charges at some point, concentrated charges or electric fields, you can actually like warp space. Like you can actually.
Yeah, very good question about warping of space, and so these are good. But if I could, following your question, I could say the following: that whenever mass, any object which has mass, it moves from place to place, it's gravitational potential energy change, right? When you move the mass from place to place, gravitational potential energy change. In the same way, whenever you move charge in electric field from place to place, then electric potential energy of that charge will change, right? So the charge moves in electric field, and mass is moving in what we say gravitational field. Okay, so instead of E is electric field, right, which we define as electric field, but that G, which is equal capital G mass, let's say, of the Earth divided by, radius, this is called gravitational field. We used to call it, in physics 1800, you call it, gravitational acceleration, 9.8, right? 9.8 meters per second squared. But formally, this is gravitational field. So instead of electric field, you have gravitational field. But the concepts are completely analogous. Very, very analogous. So again, the best summary is that if you move mass from place to place, gravitational potential energy will change. If you move charge in electric field from place to place, electric potential energy of that charge will change. And this is how you calculate the change of that potential energy. Negative of the work done by that electric force, but the work done by electric force, as I've explained, is this. Instead of F, you write Q times E. Q is constant, take it in front. And that's how you calculate in general the change of electric potential energy when the charge Q moves in the electric field from point A to B. You have to evaluate this line integral, that vector line integral, which in general is very complicated to calculate. Okay, so the change of potential energy, as you see, depends on Q, depends on what charge, how large is that charge which you move, how large in terms of the amount of charge, not the size. So that's how you calculate the change of electric potential energy in general terms when the charge moves from point A to B along any path. And that amount of potential energy will be independent of the path you take from A to B. So that path from A to B, we will be always taking the simplest, because that amount of delta U will be independent of the path, because electric force is conservative. So we will be taking charge from point A to B always along the simplest possible path, as you will see on the future slides. Okay, but that is how you calculate the change of electric potential energy in general. So that's all actually I have time to explain today, and I will devote still additional probably 3 lectures to electric potential energy, electric potential. We'll be calculating that potential energy for different situations, because you see the concept of energy is so important, because energy, total energy is conserved. So the conservation of energy is so hugely important, and potential energy is one of these energies. So we have to spend time on that and calculate this rigorously mathematically. So we will be using these line integrals. So we will be moving step by step. Don't worry, I will devote enough of time to cover all these important concepts. So this was just introductory information. It will not be included on the coming test, but on Friday, I will continue to teach about electric potential energy. But on Monday, it will be the test, and hopefully you will be well prepared to write the test. Okay, so I will now stop recording, stop sharing and stop recording.